In today's class, we are going to discuss about generation and recombination of carriers, Poisson and continuity equations, also the gate problems associated with this topic. In last two classes, we have seen about PN junction diode, Zener diode, and IC fabrications, both the theoretical part and the problematic part. Likewise, in today's class also, we are going to discuss about the charge carrier recombinations, the Poisson and continuity equations, also the problems on this particular topic. Move on to the first slide. In today's class, we are going to see the fundamentals of semiconductors. In that, the carrier diffusion, we are going to see what is diffusion current and the incident relationship. Also, how the carriers are generated and it is being recombined like an electron hole pair. And we are going to discuss about excess carrier concentrations and minority carrier recombination lifetime. First, we are going to look upon diffusion. The particles are diffused from regions of higher concentration to the regions of lower concentration due to random thermal motion. Say, in last class we have seen about the PN junction diode. When the diode is in forward bias condition, the positive terminal of the battery is being connected to the anode terminal of the diode, and negative terminal of the battery is being connected to the cathode terminal of the diode. This condition is said to be the forward bias conditions. Under this forward bias conditions, the charge carrier concentration on the higher side is tend to move to the lower concentration region because of the biasing potential that has been supplied. So here, due to the random thermal motion, the charge carriers on the high concentration region will be moved on to fill the lower concentration region with the help of this random thermal motion. This process is called as the diffusion. So diffusion means splitting out the particle from higher region to lower region. Fusion is the vice versa, that is fusion means fusing means joining or combining, that is called as the fusion process, whereas diffusion means diffusing the charged particle from the higher region to the lower concentration region. Now, this is the 1D diffusion example. The thermal random motion will cause the particle to move into an adjacent compartment every t seconds. So at every t regular time intervals, the thermal motion will make the particle to propagate into an adjacent compartment in every t seconds. Each particle will have an equal probability of jumping to the left or jumping to the right. So the above figure depicts the thermal motion process, which is allowing the charged particle to move to the adjacent compartment every t seconds. And this is the equation for the diffusion current. So the diffusion current density is denoted as J. The symbol is J to denote the diffusion current. So Jn diffusion is equal to Q is the charge, dn by dx, where capital D is the diffusion constant or diffusivity of the n-type region. So here Jn denotes the n-type material or n-type region. So in n-type region, electrons are the major charge carriers. Similarly, the current density on the p-type region or p-type material is denoted as Jp diff equal to minus Q dp by dx. So here this minus denotes the minority charge carriers compared to the majority charge carriers of the electrons, and d is the diffusivity of the p-type region. Jp is the current density of the p region layer. Look upon the graph. So here the electron will flow due to the charge carriers. So the free electron tend to flow that will constitute the flow of current in the opposite direction. So the flow of current is opposite to that of the direction of the electron flow in n-type region, whereas in p-type region, holes are the majority carriers, so it will leads to the positively charged particles that leads to the positive current. So the direction of flow of current is same as that of the direction of the flow of hole or the charge carrier particles in the p-type region. So now the total current density is given as J is equal to current density of the n-type charge carriers plus current density of the p-type charge carriers. So Jn is equal to Jn drift plus Jn diffusion, which is equal to Qn mu n epsilon plus Q dn by dx, where Q is the charge and n is the number of electrons, mu is the permeability, and epsilon is the permittivity of the n-type region. Similarly, for positive or p-type region, Jp is equal to Jp drift plus Jp diffusion is equal to Qp mu p epsilon minus Q dp by dx. So here Q is the charge and P is the number of holes and mu p is the permeability of the charge carriers, that is holes, and epsilon is the permittivity. And we know that Jp diffusion we already found out from the previous slide. So Jp diffusion is equal to minus Q dp by dx. Next, non-uniformly doped semiconductor. So doping, you know it very well because in the last two classes we have discussed about doping. Doping is nothing but the process of adding impurities in order to improve the charge carrier concentrations. Here, non-uniformly doped semiconductor, the position of EF relative to the band edges is determined by the carrier concentrations, which is determined by the net dopant concentration. In equilibrium state, EF is constant. Therefore, the band edge energies vary with position in a non-uniformly doped semiconductor. The potential difference due to N of x, P of x, the ratio of carrier densities at 2 points depends exponentially on the potential difference between these points. EF minus EI1 equal to KT ln of N1 by Ni, where EI1 is equal to EF minus KT ln of N1 by Ni. Similarly, EI2 is equal to EF minus KT ln of N2 by Ni. Therefore, EI1 minus EI2 equal to, take KT commonly outside, KT of ln of N2 by Ni minus ln of N1 by Ni, which is equal to, this Ni and Ni will be gets cancelled out. So KT ln of N2 by N1. Because so ln of N2 by Ni divided by N1 by Ni, that Ni and Ni will get cancelled. So ln of N2 by N1. Now the net voltage V is equal to V2 minus V1, which is equal to 1 by Q of EI1 minus EI2, which is equal to KT by Q ln of N2 by N1. Next, the built-in electric field due to N of x and P of x. Consider a piece of non-uniformly doped semiconductor. So this is the N-type semiconductor. It's non-uniformly doped. N is equal to Nc e power minus of Ec minus Ef by Kt. Dn by dx equal to minus Nc by Kt e power minus of Ec minus Ef by Kt into dEc by dx, which is equal to minus N by Kt, because this entire thing is replaced by N. So minus N by Kt into dEc by dx, which is equal to minus N by Kt. dEc by dx is equal to Q into epsilon. Thanks. Move on to the Einstein relationship between D and mu, diffusion and permeability. In equilibrium state, there is no net flow of charge on electrons or the holes. So the current density on n-type is 0 and p-type is also 0. The drift and diffusion current components must balance each other exactly in equilibrium state. A built-in electric field exists such that the drift current exactly cancels out the diffusion current due to the concentration gradient. Jn is equal to Qn mu n epsilon plus Qdn dn by dx is equal to 0. Similarly, Jp is equal to Qp mu p epsilon minus Qdp dp by dx is equal to 0. Already we have found this relationship. The Einstein relationship is valid for a non-degenerate semiconductor even under non-equilibrium conditions. Next. What is diffusion constant? What is the whole diffusion constant in a sample of silicon with mu p is equal to 410 centimeters square by Vs? So the answer is Kt by Q is equal to 26 millivolt at the room temperature. Next, quasi-neutrality approximation. If the dopant concentration profile varies gradually with position, then the majority carrier concentration distribution does not differ much from the dopant concentration distribution. Nd of x plus P of x is equal to Na of x plus N of x. For n-type material, N of x is nearly equal to Nd of x minus Na of x. And for p-type material, P of x is nearly equal to Na of x minus Nd of x. Now, epsilon is equal to minus Kt by Q of 1 by n dn by dx, which is equal to minus Kt by Q of this 1 by n can be replaced as 1 by Nd into dnd by dx. Next, we move on to the generation of charge carriers and recombination of charge carriers. So generation of charge carrier is generating the majority charge carriers on the n-type material, that is electrons. Similarly, on the p-type material or p-type region, it is holes. Holes are the positively charged particles, which is majority charge carriers on the p-type. And what is recombination is, on giving the bias condition or thermal condition, the electron and holes tend to move, penetrating through the potential barrier to recombine as a electron hole pair. That is called as the recombination process. The generation and recombination processes act to change the carrier concentrations and thereby indirectly affecting the current flow. So generation of charge carriers and recombination of charge carriers will act to change the carrier concentrations, then automatically it will affect the current flow indirectly. This is the generation process. So we have the two set of bands. One is electron valence band and the conduction band. On applying the thermal energy or the light, the electrons from the lower band, that is valence band, it will move on to the higher energy band, that is nothing but conduction band. This is band to band penetration, and this is RG center. So on applying the thermal energy, so the electrons from the valence band will move on to the conduction band with the help of this thermal energy that relates to the between the RG center graph. And the third graph will be showing the ionization impact moved on to the higher end layer, that is conduction band. The electrons are free to rotate or free to move to constitute the flow of current. So the recombination process, the electron from the higher end region, it will move on to the lower end region. While it is shifting from higher end region or higher concentration region to the lower concentration region, it will emit a particle or wave that is called as the light wave or photon materials. And RG centers, in silicon, the recombination of electron hole pair will be takes place via this RG centers only. Next, direct versus indirect band gap materials. Energy versus momentum diagrams. So the first one shows the direct band gap materials. Second graph shows the indirect band gap materials. In direct band gap materials, if there is a light change in momentum, the light change in momentum is required for the recombination. Momentum is conserved by the photon emission. Whereas in indirect band gap materials, the large change in momentum is allowed for the recombination of charge carriers, and here momentum is conserved by phonon plus photon emission. Phonon means sound and photon means light. The excess carrier concentration is provided as delta n is equal to n minus n naught and delta p is equal to p minus p naught. N naught and p naught are the equilibrium values at the equilibrium state. So therefore charge neutrality condition is equal to del n equal to del p, delta p. Next. Low level injection. After the disturbance from equilibrium is small, such that the majority carrier concentration is not affected significantly for an n-type material. For an n-type material. So for an n-type material, delta n is equal to delta p is very less than that of n naught, where n is nearly equal to n naught. For a p-type material, delta n is equal to delta p is very less than that of p naught, so p is nearly equal to p naught. However, the minority carrier concentration can be significantly affected by the recombination process. Next, indirect recombination rate. Suppose excess carriers are introduced into an n-type silicon sample at time t equal to 0. How does p vary with the time t is greater than 0? Consider the rate of fold recombination via traps dou p by dou t equal to minus Cp nt into p. Under low level injection conditions, the whole generation rate is not significantly affected. Dou p by dou t g or dou p by dou t g in equilibrium state equal to minus dou p by dou t in R equilibrium state, which is equal to Cp nt rho naught. The net rate of change in P is therefore dou P by dou T Rg graph equal to dou P by dou T into R by R plus dou P by dou T G equal to minus Cp nt P plus Cp nt P naught. Now dou P by dou T Rg gap equal to minus Cp nt P minus P naught equal to minus delta P by tau P. The tau P is equal to 1 by Cp nt. Next, move on to the minority carrier recombination lifetime. The tau p is equal to 1 by Cp nt, tau n is equal to 1 by Cn nt. The minority carrier lifetime tau is nothing but the average time is required for an excess minority carrier survives in a majority carrier layer. The value of tau will ranging from 1 nanosecond to 1 millisecond in silicon and depends upon the density of the metallic impurities, that is the contaminants, such as Au, gold and platinum, and the density of crystalline defects. These impurities will give rise to the localized energy states deep within the band gap. Such deep traps capture electrons or holes to facilitate recombination, and it's also called recombination generation center. Recombination generation centers. Next. Relaxation to the equilibrium state. Consider a semiconductor with no current flow in which thermal equilibrium is distributed by the sudden creation of excess holes and electrons. The system will relax back to the equilibrium state via the Rg mechanism. Now dou n by dou t is equal to minus delta n by tau n for electrons in the p-type material. Now dou p by dou t is equal to minus delta p by tau p for holes in the n-type material. Last, we are going to see with an example, that is photoconductor. Consider a sample of silicon doped with 10 power 16 centimeter cube boron with recombination lifetime of 1 microseconds. It is exposed continuously to light such that electron hole pairs are generated throughout the sample at the rate of 10 power 20 per centimeter cube per second. That is, the generation rate GL is equal to 10 power 20 per centimeter cube per second. What are P naught and N naught? What are delta N and delta P? What are P and N, and what is the NP product? So for that, the arbitrary injection levels, the net rate of carrier recombination is minus dou delta N by dou T equal to minus dou delta P by dou T, which is equal to Pn minus Ni square divided by tau P of N plus N1 plus tau N of P plus P1. Now, this N1 is equal to Ni into e power of Et minus Ei by Kt, and P1 is equal to Ni e to the power of Ei minus Et by Kt. Now, coming to the summary. So far, we have seen about the electron hole concentration gradient diffusion process. So, Jn diffusion of n-type material equal to Qdn dn by dx, and Jp diffusion equal to minus Q dp by dp by dx. Next, we have seen the current flowing in a semiconductor is a compromised of drift and diffusion components for both the electrons and holes. J is equal to Jn drift plus Jn drift plus Jp drift plus Jp drift. In equilibrium state, Jn is equal to Jn drift plus Jn diff equal to 0, and Jp is equal to Jp drift plus Jp diff is equal to 0. The characteristic constant of drift and diffusion are related. D by mu equal to Kt by Q. And we have seen generation and recombination RG process affect carrier concentration as a function of time, and thereby the current flow will be disturbed. So the generation rate is enhanced by deep states due to defects or impurities, and also by high electric field. The recombination in silicon is primarily via recombination and generation of charge carriers at centers. The characteristic constant for indirect RG is the majority lifetime carrier. Tau P is equal to 1 by Cp Nt for n-type material, and tau N is equal to 1 by Cn Nt for p-type material. Generally, the net recombination rate is proportional to Np minus Ni square. With this, the theoretical part of this charge carriers, generation of charge carriers and recombination of charge carriers, the current density and band gap, carrier lifetime and recombination rate, recombination generation process, everything we have covered. I hope so you have understood clearly. If you have any doubts, you would then and there interrupt me. Next, move on to the practice questions based on this topic. Here, the first question is, a region of negative differential resistance is observed in the current voltage characteristics of a silicon PN junction if the options are both the P and N region are heavily doped, the N region is heavily doped compared to the P region, the P region is heavily doped compared to the N region, and intrinsic silicon region is inserted between the P region and the N region. Here, what is the question? A region of negative differential resistance is observed in the current voltage characteristics of a silicon PN junction if the option is A, the correct answer is A, it is both the P region and N regions are heavily doped. If both P and N regions are being heavily doped, added with a heavy impurities, what happens? The potential barrier region width will be thin. So, a negative differential resistance will be observed in the current voltage characteristics of a silicon PN junction if both the P and N-type material are heavily doped. Next question. The built-in potential for an abrupt PN junction is 0.75 volt. If a junction capacitance at a reverse bias of 1.25 volt is 5 picofarad, the value of junction capacitance when VR equal to 7.25 volts. The answer is 2.4 to 2.6. Next. For a silicon diode with long P and N regions, the acceptor and donor impurity concentrations are 1 into 10 to the power 17 centimeter cube and 1 into 10 to the power 15 centimeter cube respectively. The lifetime of electrons in P region and holes in N region are both 100 microseconds. The electron and hole diffusion coefficients are 49 centimeters square per second and 36 centimeters square per second respectively. Assume Kt by Q is equal to 26 millivolt. The intrinsic carrier concentration is 1 into 10 to the power 10 centimeter cube and Q equal to 1.6 into 10 to the power minus 19 coulombs. When a forward voltage of 208 millivolt is applied across the diode, the whole current density injected from P region to N region is 28 to 30. Next. The electric field profile in the depletion region of a PN junction in equilibrium is shown in the figure. Which one of the following statement is not true? That means which one of the following statement is false? The left side of the junction is N-type and right side is P-type. Both the N-type and P-type depletion regions are uniformly doped. The potential difference across the depletion region is 700 millivolt. If the P-type has a doping concentration of 10 to the power 15 centimeter cube, then the doping concentration in N-type region will be 10 to the power 16 centimeter cube. The correct answer is the potential difference across the depletion region is 700 millivolt. Next. A silicon PN junction is forward biased with a constant current at room temperature. When the temperature is increased by 10 degrees Celsius, the forward bias voltage across the PN junction is, options are, increases by 60 millivolt, decreases by 60 millivolt, increases by 25 millivolt, decreases by 25 millivolt. The correct answer is decreases by 25 millivolt. Next question. Compared to a PN junction with Na and Nd concentrations 10 power 14 centimeter cube, which one of the following statement is true for a PN junction with Na and Nd equal to 10 to the power 20 centimeter cube? The options are reverse breakdown voltage is lower and depletion capacitance is lower. Reverse breakdown voltage is higher and depletion capacitance is lower. Reverse breakdown voltage is lower and depletion capacitance is higher. Reverse breakdown voltage is higher and depletion capacitance is higher. The answer is option C. The reverse breakdown voltage is lower and depletion capacitance is higher. Next. Which of the following is not associated with the PN junction diode? The options are junction capacitance, charge storage capacitance, depletion capacitance, and channel length modulation. The correct answer is channel length modulation. Next, consider the following statement. S1, for Zener effect to occur, a very abrupt junction is required. For quantum tunneling to occur, a very narrow energy barrier is required. Which of the following is correct? Only S2 is true. Both S1 and S2 are true, but S2 is not a reason for S1. Both S1 and S2 are true. S2 is a reason for S1. Both S1 and S2 are false. The option correct answer is only S2 is true. Next. In a P plus N junction diode under reverse biased, the magnitude of electric field is maximum at, the options are, edge of the depletion region on the P side, edge of the depletion region on the N side, the P plus N junction, center of the depletion region on the N side. The correct answer is option C, P plus N junction. Next. A P plus N junction will have a built-in potential of 0.8 volt. The depletion layer width at a reverse bias of 1.2 volt is 2 micrometer. For a reverse bias of 7.2 volt, the depletion layer width will be 4 micrometer, 4.9 micrometer, 8 micrometer, and 12 micrometer. The correct answer is 4 micrometer. Next. The group 1 lists 4 types of PN junction diodes. Match each device in group 1 with one of the option in group 2 to indicate the bias condition of the device in its normal mode of operation. So the group 1 is Zener diode, solar cell, laser diode, avalanche photodiode. Group 2 is forward bias and reverse bias. So the options are P1, Q2, R1, S2, P2, Q1, R1, S2, P2, Q2, R1, S1, P2, Q1, R2, S2. The correct answer is option B, P2. P is Zener diode, reverse bias, and Q1, solar cell in forward bias, R1, laser diode in forward bias, and avalanche photodiode in reverse bias. Next. This already we have seen. Next. So the following problems we are going to see based on the minority charge carrier diffusion for electrons. Here, the sample is uniformly illuminated with light, resulting in an optical generation rate GL is equal to 10 to the power 20 centimeter cube per second. Find the steady state excess minority carrier concentration and the QFLS and FN and FP. Assume spatially uniform conditions and approach the problem as follows. The solution is simplify the minority carrier diffusion equation for this problem. Begin with dou delta n by dou t is equal to dn d square delta n by dx square minus delta n by tn plus gl. For steady state, simplifying it, 0 is equal to dou delta n by dou t equal to 0, which is equal to dn d square delta n by dx square minus delta n by tau n plus gl. Okay. For spatially uniforming conditions, this dn delta square delta n by dx square is also 0. So 0 is equal to 0 minus delta n by tn tau n plus gl. Therefore, gl is equal to tau delta n by tau n or minus delta n by tau n plus gl equal to 0. Next. Specify the initial and boundary conditions as appropriate for this problem. Since the solution is, since there is no time dependence, there is no initial condition, hence there is no spatial dependence, there are no boundary conditions. Next. Solve the problem. In this case, the solution is straightforward. Delta n equal to GLT tau n equal to 10 to the power 20 into 10 power minus 6 equal to 10 power 14 centimeter cube. Now compute the QFLS. Since we are doped p-type and in low level injection, P is directly proportional to P naught, which is equal to Na equal to N1 e to the power Fi minus Fp by Kp by Kpt. Kbt. Fe is equal to Ei minus Kb T ln of Na by Ni, which is equal to Ei minus 0.026 ln of 10 to the power 17 by 10 to the power 10 equal to Ei minus 0.41 electron volt. For n is nearly equal to delta n is very greater than n naught, which is equal to Ni into e to the power Fn minus Ei by Kbt, where Fn is equal to Ei plus Kbt ln of delta n by Ni, which is equal to Ei plus 0.026 ln of 10 to the power 14 by 10 to the power 10 equal to Ei plus 0.24 electron volt. Note that since we are using the MCDE, we are assuming low level injection. We should check the assumption that delta n is very less than P from the solution and the given p-type doping density. We have delta n is equal to 10 to the power 14, very less than that of P equal to 10 to the power 17. We are indeed in low level junction. Provide a sketch of the solution and explain it in words. So the excess carrier density is constant, independent of position. So the QFL, they are split because we are not in equilibrium state. The whole QFL is essential where the equilibrium Fermi level was, because the whole concentration is virtually unchanged, but the electron QFL is much closer to the conduction band because there are orders of magnitude more electrons. Next question. The sample has been uniformly illuminated with light for a long time. The optical generation rate is GL is equal to 10 to the power 20 centimeter cubes per second. At time t equal to 0, the light is switched off. Find the excess minority charge carrier concentration and the QFL versus time. Assume spatially uniform conditions and approach the problem as follows. First, simplify the minority carrier diffusion equation for this problem. So we know that dou delta n by dou t equal to dn d square delta n by dx square minus delta n tau n by tau n plus gl. For spatially uniform conditions with no generations, so dou delta n by dou t equal to minus delta n by tau n, whereas this dn d square delta n by dx square plus gl, this is 0. Specify the initial and boundary conditions as appropriate for this problem. There is no spatial dependence and there is no need to specify boundary conditions. So the initial condition is delta n of t equal to 0 equal to 10 to the power 14 centimeter cube. Next, d delta n by dt equal to minus delta n by tau n. So the solution is delta n of t equal to a into e to the power minus of t by tau n. Using the initial condition, delta n of t equal to 0, which is equal to 10 to the power 14 equal to a. So delta n of t equal to 10 to the power 14 into e to the power minus of t by t tau n. Next. Provide a sketch for the solution and explain it in words. So this is the diagrammatic flow for the electrons QFL. Fn of t equal to ei plus kbt ln of delta n of t plus n naught by ni. Initially, delta n of t is very greater than that of n naught, and delta n of t equal to delta n of 0 e to the power minus t by tau b. So Fn of t initially drops linearly with time towards Ef. Next question. The sample is uniformly illuminated with light, resulting in an optical region generation rate. GL is equal to 10 to the power 20 centimeter cube per second. The minority carrier lifetime is 1 microsecond, except for a thin layer 10 nanometer wide near x equal to 0, where the lifetime is 0.1 nanosecond. Find the steady state excess minority carrier concentration and QFL versus position. You may assume that the sample extends to x equal to plus infinity. Treat the thin layer at the surface as a boundary condition. Do not try to resolve delta n of x inside this thin layer. You approach the problem as follows. So begin with the solution using the minority carrier diffusion equation. We know that dou delta n by dou t is equal to dn d square delta n by dx square minus delta n by tau n plus gl. The first step is we have to simplify for the steady state conditions. So this dou delta n by dou t is equal to 0. We know that. So 0 is equal to dn d square delta n by dx square minus delta n divided by tau n plus gl. The simplified minority carrier diffusion equation is dn d square delta n by dx square minus delta n by tau n plus gl equal to 0, or d square delta n by dx square minus delta n by ln square plus gl by dn equal to 0, and ln is equal to root of dn by, into tn. Now d square delta n by dx square minus delta n by ln square plus gl by dn equal to 0, where ln is equal to root of dn tau n. That is the minority carrier diffusion length. Last, specify the initial and boundary conditions appropriate for this problem. Since this is a steady state problem, there is no initial condition. As x tends to the infinity, we have a uniform semiconductor with a uniform generation rate. In a uniform semiconductor under illumination, delta n is equal to gl into tau n. So delta n of x tends to infinity, which is equal to gl into tau n. In the thin layer at the surface, the total number of electron hole pairs recombining per centimeter square per second is the recombination rate per centimeter cube per second, which is r is equal to delta n of 0 by tau s per centimeter cube per second times the thickness of the thin layer at the surface. Delta x in centimeter. If we multiply these two quantities, we get the total number of magnetic carriers recombining per centimeter square per seconds in the surface layer, which we will call as Rs. Now this Rs is equal to integral of 0 to delta x r of x dx, which is nearly equal to delta n of 0 by tau s into delta x centimeter square per second. Rearranging this equation, we can write Rs is equal to del x by tau s into delta n of 0, which is equal to Sf delta n of 0 centimeter square per second, where Sf is equal to delta x by tau s into per centimeter per second. It is Sf is a quantity with the units of velocity. In practice, we usually don't know the thickness of the low lifetime layer at the surface or the lifetime in this layer. So instead, we just specify the front surface recombination velocity. Typically, 0 less than Sf less than or equal to 10 to the power 7 centimeters per second. For this specific problem, Sf is equal to delta x divided by tau s, which is equal to 10 to the power minus 6 centimeter by 10 to the power minus 10 seconds, which is equal to 10 to the power 4 centimeter per second. The surface recombination velocity is simply a way to specify the strength of the recombination rate at the surface. Rs is equal to delta x by tau s, where delta n equal to 0, delta n of 0, which is equal to Sf delta n of 0 centimeter square per second. One second. Next question. In a steady state, carriers must diffuse to the surface at the same rate that they are recombining so that the excess magnetic carrier concentration at the surface stays constant with time. Then the diffusion current of electron at the surface is Jn is equal to Q dn d delta n by dx ampere per centimeter square, Armstrong per centimeter square. The flux of the electron in the positive x direction is Jn by minus Q equal to minus dn d delta n by dx centimeter square per second. The flux of the electrons in the x direction to the surface where they are recombining is minus of Jn by minus Q, which is equal to plus dn d delta n by dx centimeter square per second. In steady state, this flux of electrons flows to the surface at exactly the same rate as that they combine at the surface. So the boundary condition is plus dn delta d delta n by dx where x equal to 0, where Rs is equal to Sf delta n of 0. Solve the problem. D square delta n by dx square minus delta n by L square ln square plus gl by dn equal to 0. To solve this homogeneous problem, first we have to set gl equal to 0. So d square delta n by dx square minus delta n by dln square equal to 0. The absolute solution is delta n of x equal to a to the power a into e to the power minus of x by ln plus b into e to the power plus x by ln. For a particular solution, letting x tends to the infinity, where everything is uniform. Therefore, minus delta n by ln square plus gl by dn equal to 0. The solution is delta n equal to minus ln square divided by dn into gl, which is equal to gl into tau n. gl into tau, where tau n is equal to minus ln square by dn. Add these two solutions, delta n of x equal to a into e to the power minus of x by lx plus b into e to the power plus x by ln plus gl into tau n. To satisfy the first boundary condition as x tends to infinity b equal to 0, now consider the boundary condition at x equal to 0 plus dn d delta n by dx where x equal to 0 equal to minus dn by ln a equal to sf del n of 0 equal to sf a plus gl tau n, where a equal to minus sf gl tau n by dn by ln plus sf, which is equal to minus gl tau n by 1 plus dn by ln by sf. Delta n of x equal to gl tau n of 1 minus e to the power minus x by ln by 1 plus dn by ln by sf. So based on the condition when SF equal to 0 centimeter per second, which implies that there is no recombination at the surface, then we find del n of x equal to GL tau n, which makes sense since we have spatial uniformity. SF tends to infinity. Strong recombination at the surface should force delta n of x equal to 0 equal to 0. But in the bulk, we should still have del n of x equal to GL tau n. The transition from 0 to a finite value in the bulk should take a diffusion length of 2. So from the solution, delta n of x equal to GL tau n of 1 minus e power minus of x by ln by 1 plus dn by ln by sf. When sf tends to infinity, we find ln of x equal to GL tau n into 1 minus e to the power minus x by ln. This part dn by ln by sf will be vanished. One since sf tends to infinity, 1 by infinity will be 0. So you'll be having GL tau n of 1 minus of e power minus x by ln by 1. So 1 minus of e power minus x by ln. So last, drawing the graph for the above problem. So the concentration is, we know that GL tau n in the bulk, but less at the surface because of surface recombination. The transition from the surface to the bulk takes place over a distance that is a few diffusion length long. The whole QFL is constant and almost exactly where the equilibrium Fermi level was, because we are in low level injection. But the electron QFL is much closer to the conduction band edge. It moves away from EZ near the surface because surface recombination reduces del n of x near the surface. The variation with position is linear because del n of x varies exponentially with position. Next. The sample is in the dark, but the excess carrier concentration at x equal to 0 is held constant at del n of 0 equal to 10 to the power 12 by centimeter cube. Find the steady state excess minority carrier concentration and QFL versus position. So you may assume that the sample state extends to x equal to the plus infinity. Make reasonable approximations and approach the problem as follows. So here, foremost we have to do that minority carrier diffusion equation to be simplified. So we know that dou delta n by dou t equal to dn d square delta n by dx square minus delta n by tau n plus gl. Now dou delta n by dou t is 0. So now 0 is equal to dn d square delta n by dx square minus delta n by tau n plus gl. So there is no generation of transfer carrier, so GL equal to 0. The simplified minority carrier diffusion equation is dn d square delta n by dx square minus delta n by tau n equal to 0 because this GL is 0. Okay, or d square delta n by dx square minus delta n by dn tau n equal to 0, or ln equal to root of dn tau n. So d square delta n by dx square minus delta n by ln square equal to 0, where ln is equal to root of dn tau n is the minority carrier diffusion length. Specify the initial and boundary conditions as appropriate for this problem. Since this is a steady state problem, there is no initial conditions. As x tends to the infinity, we expect all of the magnetic carriers to have recombined. So del n of x tends to the plus infinity equal to 0. At the surface, the excess electron concentration is held constant. So del n of x equal to 0 equal to 10 to the power 12 centimeter cube. So d square delta n by dx square minus delta n by ln square equal to 0. The solution is delta n of x equal to a into the e power x by ln plus b into the e power plus x by ln. This we know it right from the previous problems. To satisfy the first boundary condition, b equal to 0. So now consider the second, delta n of 0 equal to 10 to the power 12 centimeter cube. So delta n of x equal to delta n of 0 into the e to the power minus x by L1 equal to 10 to the power 12 into e to the power minus x by L1. So now provide a sketch for this above equation. So this is the diagrammatic part for the above problem. So likewise, we have the same pattern problems we just move on to the some other pattern problems, so that it will be useful for you to understand some more problems in a better way. Now look upon this problem. It concerns a PN junction doped Na equal to 2 into 10 to the power 18 centimeter cube. So they have given a concentration on the N type. On the P side, Nd equal to 3 into 10 to the power 17 centimeter per cube on the N side. I answer the following questions. There is an inbuilt potential for this PN junction. Which side is more positive, the P side or the N side? Explain your answer. So they have given the doping concentration, charge carrier concentration on both the P type and the N type. In this PN junction, we have to find out there is a inbuilt potential is there. We have to identify which side is more, either positive side, P side or N side. So now look upon the diagram. The holes will be diffusing from the left to the right side, and electrons electric field will be stating from the right to the left side. So if the electric field points from the right to the left, the right side, the inside is more positive. This inside is more positive. Next. Assume that the PN junction is made up of silicon. What is the magnitude of the inbuilt potential? So that you may assume that Nc is equal to 3.23 into 10 to the power 19 per centimeter cube. Now Nv is equal to 1.83 into 10 to the power 19 per centimeter cube, and Na is equal to 1 into 10 to the power 10 per centimeter cube, and Eg is equal to 1.125 electron volt. Now the inbuilt potential VBA equal to KBT by Q ln of Na Nd by Na square, which is equal to 0.026 ln of 2 into 10 to the power 18 into 3 into 10 to the power 17 by 10 into 10 power 20, which is equal to 0.95 volt, where VBA equal to 0.95 volt. Assume that the PN junction is made of gallium arsenide. What is the magnitude of the inbuilt potential? So that you may assume that Nc is equal to 4.21 into 10 to the power 17 per centimeter cube. Nv is equal to 9.52 into 10 to the power 18 per centimeter cube. Na is equal to 2.25 into 10 to the power 6 per centimeter cube, and Eg is equal to 1.422 electron volt. VBI equal to KBT by Q ln of Na Nd by Na square equal to 0.026 ln of 2 into 10 to the power 18 into 3 into 10 to the power 17 by 2.25 into 10 to the power 16 the whole square is equal to 1.38 volt. Compare your answers in 1B and 1C to the corresponding band gaps. So now the solution is energy band gap of silicon equal to 0.95 volt minus 0.8 Eg of electron volt. VBI gallium arsenide equal to 1.38 volt equal to 0.797 Eg of electron volt. So the inbuilt potential of a PN junction is typically little lesser than that of the band gap of the semiconductor in electron volt. Now derive the expression that relates to VBI to Eg. VBI equal to KBT by Q ln of Na Nd by Na square, where Na square equal to Nc Nv e to the power minus Eg by KBT. And VBI equal to KBT by Q ln of Na Nd by Nc Nv e to the power minus Eg by KBT equal to KBT by Q ln of Na Nd by Nc Nv plus KBT by Q ln of e to the power Eg by KBT. And VBI is equal to KBT by Q ln of Na Nd by Nc Nv plus Eg. VBI equal to Eg minus KBT by Q ln of Nc by Nd minus KBT by Q ln of Nv by Na. For a non-degenerative semiconductor, P naught equal to Na is less than Nv and N naught equal to Nd less than Nc. So the inbuilt potential is a little less than that of the band gap. This is the energy band gap diagram. So in this, the potential at x equal to 0 more or less positive than the potential at x equal to L. So the potential at x equal to 0 point is more than that of the potential at the point x equal to L. We have to compare and see. So a positive potential over the band at x equal to 0 EC is lower than at x equal to L. So the potential at x equal to 0 must be more positive than the potential at x equal to L, because at the lower band at x equal to 0, the positive potential will be occurred. Okay, this positive potential will be occur. Whereas at the higher level, x equal to L, the negative potential or less potential will be appeared than that of the lower potential range. What is the magnitude of the inbuilt potential? EI is equal to x equal to L by Q, which is equal to EF by Q plus 0.025. EI of if x equal to 0 by Q equal to EF by Q minus 0.030. VBA equal to EI of x equal to L by Q minus EI of x equal to 0 by Q, which is equal to 0.025 plus 0.030 equal to 0.055 volt, where VBA equal to 0.055 volt. We'll see the another problem. Assume silicon band gap 1.12 electron volt at room temperature 300 Kelvin with the Fermi level located exactly in the middle of the band gap. Answer the following questions. What is the probability that a state located at the bottom of a conduction band is filled? What is the probability that a state located at the top of the valence band is empty? Begin with the Fermi function f of E equal to 1 by 1 plus e to the power of E minus Ef by kb t. So in our problem, E equal to EC. So f of EC is equal to, this E will becomes f of EC 1 divided by 1 plus e to the power of, instead of E, we substitute EC minus EF by kBt, which is equal to, nearly equal to e to the power minus of EC by EC minus EF by kBt. The approximation is extremely good because the bottom of the conduction band is very far above the Fermi level. The semiconductor is said to be non-degenerative. EF is equal to EC plus EB by 2. The Fermi level is exactly in the middle of the band gap. EC minus EF equal to EC minus EC plus EB by 2, which is equal to EC minus EB by 2 equal to EG by 2. So the probability is f of EC is nearly equal to e to the power minus of EC minus EF by kBt, which is equal to e to the power minus EG by 2 kBt. Now EG is equal to 1.12 electron volt, kBt equal to 0.026 electron volt. Now EG by 2 kBt equal to 21.5. F of EC is equal to e to the power minus EG by 2 kBt equal to e to the power minus of 21.5 equal to 4.43 into 10 to the power minus 10. What if we had not made the non-degenerative approximation? Then f of EC is equal to 1 divided by 1 plus e to the power EC minus EF by kBt, which is equal to 4.43 into 10 to the power minus 10. It is the same answer as with the non-degenerative assumption. And begin again with the Fermi function f of e equal to 1 divided by 1 plus e to the power e minus ef by kBt. Now here instead of EC, you substitute e is equal to EV. F of EV equal to 1 divided by 1 plus e to the power EV minus ef by kBt. Repeating on the same procedure, here also we will be calculating the EV equal to EG by 2, similar to that of previous one. So the probability is 1 minus f of EV equal to e to the power minus of EF minus EV by kBt, which is equal to e to the power minus EG by kBt. So 1 minus f of EV equal to 4.43 into 10 to the power minus 10. With this, I will wind up the class today. I hope so you have understood the charge carrier generation and recombination, the current density equations. Then we have seen the energy band concentrations, the equations associated with this energy band concentrations. So far everything we have discussed. I hope so you have clearly understood this. If you have queries, you can post it in the chat box. So we will continue in the next class. With this, I will wind up the class today. Thank you all.